This is harmonics impact on power quality with MATLAB applications. So here, basically, wherever we go, we search for quality, whether it is any kind of work or any kind of our livelihood, wherever we go for quality. We search for quality. So that's what the power what we received, or what the power is being consumed by us, it should be of quality in nature. But due to some nonlinearities present in the system, and these nonlinearities will lead to the production of harmonics, which are unwanted, non-sinusoidal components, So these things we have to discuss, and we have to focus more on these things, and why these are coming, why these are generating, and what are the sources, and how these things should be mitigated. And of course, by using a simple MATLAB application, I would like to elaborate more. So basically, this today's session, I would like to discuss the basic power quality issues, a harmonic introduction, sources of harmonics, effect of harmonics, solutions, and the harmonic Fourier representation, and some other key points. And all these things I would like to focus. So before going to this, what are the basic issues regarding power quality? Why the power quality is getting degraded, and what are the basic issues regarding this power quality? If we take up the power quality issues would be these, as per this particular document, 1159/2009 IEEE. This is the recommended practice for monitoring electric power utility. So these are all the kind of terms and terminology associated in the power quality. So basically, we are having these kind of issues as far as power quality. Out of these, harmonics is one of the issues, one of the major issues where we have to concentrate more. So out of these, basically, first we would like to have the power quality issues, like what is meant by flickers, flickering, so unbalance in the system, sags, swells, transients, interruptions, so frequency deviations, harmonics, over and under voltages. So before going to this, let us see the details of each and every one. Okay, each and every one. So the first one is flickers. As we have seen, flickers. So flickering is when voltage changes occur in rapid succession. So if the voltage changes occur in a rapid succession, in a rapid manner, if the voltage variations have been taking place in a rapid manner, then it is said to be flicker. So voltage unbalance. The second aspect is voltage unbalance. So whenever there is, if we take up a three-phase system, whether it is a star connected or delta connected system, if the impedances Z1 at an angle phi1 is not equal to Z2 at an angle phi2 is not equal to Z3 at an angle phi3, then the corresponding loads will be different. Naturally, there will be the voltage imbalance. Voltage imbalance as far as the load point of view is concerned. And similarly, during any fault that occurs on a balanced three-phase system, it leads to there is a magnitude of line or phase voltages are different. It causes the different magnitudes of line or phase voltages, so which leads to the voltage imbalance, The next one is these causes, these unbalanced voltage. What are the causes for these unbalanced voltages? These are due to mechanical stresses in motors, mechanical stresses that are present in the motors, and higher than the normal current, the normal rated current when the motor draws due to any problems, and unbalanced current that will flow in the neutral conductor of a three-phase star connected system. These are all lead to the unbalanced voltages, the unbalance in the voltages. So next, the one of the power quality issue is voltage sag. Voltage sag. So this is a voltage dip. This is a voltage dip or a short duration reduction in the RMS voltage. A short duration reduction in the RMS voltage. So these are all the power quality issues. So this voltage sag happens when the RMS voltage decreases between 10 and 90% of the nominal voltage. So there is a decrement in the reduction of the RMS voltage of the waveform, and this decrement in the voltage should be of the order of 10 to 90%. It should be of the order of 10 to 90%. Then it is termed as a voltage sag. Then you have we have voltage swell. So this is defined as per IEEE 1159. This is nothing but an increase in the RMS voltage, level up to 110% to 180% of the nominal value. The duration is also mentioned, and this duration is half cycle to 1 minute. For a duration of half cycle in the sense, if it is a 50 Hz system, it would be 10 milliseconds. During the course of 10 milliseconds to 1 minute, if the RMS voltage level of 110% to 180% is maintained, and that too the increase in the RMS voltage, then it is termed as voltage swell. This also comes under the power quality issue. So swells can occur when large load is turned off and voltage on the power line increases for a shorter period of time. The causes why voltage swells do occur. So these voltage swells do occur when large load is turned off. The load is removed. When the load is removed, large load is removed, and voltage on the power line increases for short period of time. Next, apart from these, we are having transients. Transients are also we are having. These are momentary bursts of energy induced upon power, data, or communication lines. So the transients, basically these are two types as per IEEE 1159/2019 standards. These are defined as impulsive and oscillatory types. So an impulsive transient would be a lightning transient or electrostatic discharge. This is the lightning one. Due to lightning, an impulse, impulse waveform. At time t equal to 0, it rises sharply. At time t equal to 0, it rises sharply to a peaky value. That's the nature of the impulse work. So the example of an impulse transient would be a lightning transient or electrostatic discharge. So why do these transients occur? So switching of facility loads. So loads on and off times, opening and closing of disconnects are energized lines whenever the energized lines are opened or closed. And switching of capacitor banks when the capacitor banks are switched on, and the reclosures, we know the circuit breaker reclosure operations, and tap changing on transformers. So these are all the causes of these transients, which are a part of these power quality issues. Which are all the part of power quality issues. So next, we have seen interruption. So how an interruption is defined? So this is also defined as a decrease in the voltage supply level to less than 10% of the nominal. If it is 10% of the nominal value, the decrease in the voltage supply level to less than 10% of the nominal value, then it is said to be an interruption. Simply, it is called an interruption. An interruption. Next, we are going to have frequency variations. So the deviation from the nominal supply frequency, of course, the frequency deviation will be tolerated. If it is a 50 Hz system, it can be tolerated up to 49.95 to 50.05 Hz. Up to that, it can be tolerated. But we see in the case of load frequency control, when the load on the system goes on increasing, the frequency goes on decreasing. So there is load frequency control. In the case of load frequency control, what we have seen in the case of power system operation and control, if the frequency raises, the turbine reduces its input. That is the steam input. This is how the load frequency control mechanism works. So the frequency variations is nothing but a deviation from the nominal supply voltage. These deviations can be tolerable up to say 0.5. So 49.95 to 50.05 it is allowed. If it is beyond that, there are other problems associated. So next, going to the harmonics. So what is a harmonic? So in an electrical power system, a harmonic of voltage or current waveform is a sinusoidal wave whose frequency is an integer multiple of fundamental frequency. So fundamental frequency sin omega t, if we take up, if we have an integral multiple of this fundamental frequency, so then we call it as whether it is a voltage or current, then it is said to be a harmonic wave. The harmonic frequencies are produced by the action of non-linear loads. What are the examples of non-linear loads? We'll be having the rectifiers. So discharge lightning, saturated electrical machines in the sense, if you take up the saturation curve of a DC generator or an alternator. So at the time of starting, if you go on increasing the excitation, that is, if you go on increasing the flux, the corresponding EMF that is generated will be linear up to certain extent. At a point where what we call a knee point, K-N-E-E, knee point. When we reach that knee point, beyond that, if you go on increasing the excitation current, or if you go on increasing the flux, the corresponding EMF would not go linear way. It goes in a non-linear way. That's what it comes into saturation. The machine enters into saturation. So this saturation of the machines leads to the harmonics. So saturation of the machines, they lead to harmonics, and discharging of the lights, discharging phenomenon, the lightning discharging phenomenon also leads to the generation of harmonics, and the rectifiers which converts AC to DC, they also a source of harmonics. Basically, wherever we find the power electronic components, and also the magnetic core in the electrical machines. In the electrical machinery, the energy conversion takes place through magnetic medium. So wherever the magnetic core is present, there the production of harmonics, or there the generation of harmonics will be taking place. So that's how. So they are a frequent cause of power quality problem, these harmonics also, and can result in increased equipment and conductor heating. Due to these harmonics, the heating of the equipment may take place. It results in more heating of the equipment and misfiring. Misfiring may take place in variable speed drives. Variable speed drives applications, we find misfiring, and torque also pulsates. So it is not maintained constant, but it goes on pulsating. The torque pulsations may take place in the case of motors and generators. And also, apart from this, we will be having over voltages. Apart from the harmonics, we are going to have the over voltages. So these are those voltages that exceed the normal or rated values, which cause insulation damage to the electrical appliances. So those which cause insulation damage, the over voltages, they cause insulation damages. So over voltage, if you take up as per IEEE, an increase in the AC voltage, AC RMS voltage, 110% to 120% of the nominal at the power frequency for a duration longer than 1 minute. So long duration, longer than 1 minute, in the sense this is a longer, this is a long duration voltage, over voltage, long duration over voltage. So these occur mainly because either the voltage controls are inadequate or the system is too weak for voltage regulation. So to have the control over the voltage, or to have more voltage regulation in the system becomes weak, these do occur. These over voltages do occur. And apart from this, we will be having under voltage conditions. So these under voltage also the reduction in the level of voltage, which drastically reduce the life of the electromechanical equipment. The life of the electromechanical equipment gets reduced by these things. So these under voltages increase the operating current. So whenever the voltage reduces for a given power P equal to, if you take up V into I, maintaining the power factor is unity. If the voltage gets reduced under voltages, the current gets increased. So this increases the operating current, causing overheating, which will shorten the life of the machine, the life of the particular equipment. So next we will be having the transients, which are also a part and parcel of our quality issues. So these are due to lightning surges and switching surges. Two main sources of transient over voltages on utility systems are basically capacitor switching and lightning. Due to capacitor switching actions and due to lightning, we are having the sources of transients. So these effects of transients are, they degrades the insulation of the motor winding, resulting to equipment failure. These are the, so degradation, these degrade the insulation of the motor, which results the equipment failure. So these are all the things what we are supposed to have in the case of power quality issues. Power quality issues are concerned. So these are all the things what we are supposed to have, like what we have mentioned, the flickers, the unbalance in the voltages, sags, swells, transients, interruptions, frequency deviations, of course harmonics, over and under voltages. So these are all the things associated, these are all the terms, these are all the issues, what we say, these are all the issues associated with the power quality. power quality, and I have given the basic things, the basic knowledge regarding all these issues. So as far as the power quality is concerned, as far as the power quality is concerned, according to utility point of view is concerned, a power quality is the reliability. Reliability means whenever power is needed, it should be supplied. Whenever power is needed, it should be supplied. So according to utility point of view, the power quality is defined as reliability. Power quality is nothing but reliability. Whenever the power requirement is there, it should be supplied, should be in a position to supply the power. According to load aspect, if we take up the load aspect, there should be satisfactory performance of all the equipment. So whatever the loads you are connecting in the system, they should be satisfactorily operated. All the equipment which are connected as the load, they should be satisfactorily operated. Right? That is, all the sensitive equipment should be satisfactorily operated as per the load aspect point of view. In one view, different views, the power quality finds its own definitions in different manners like this. If it is in the point of utility point of view, it is the reliability. If it is a load aspect, it should be in a position to give satisfactory performance. It should be in a position to give satisfactory performance for all the equipment. So if the end user consumer point of view is concerned, if we take up the consumer point of view, it is defined as any power problem manifested in voltage, current or frequency deviations that result in failure of misoperation of the customer operation. So any particular problem, as far as the end user or the consumer point of view is concerned, any power problem which is manifested by means of voltage, current or frequency deviations that result in failure or misoperation of customer operation. As far as IEEE dictionary, it is defined as the concept of powering and grounding sensitive equipment in a manner that is suitable to the operation of that equipment. A simple definition. The concept of powering and grounding sensitive equipment, powering equipment and grounding sensitive equipment in a manner that is suitable to the operation of that equipment. Next, we have IEC, International Electrochemical Commission. International Electrochemical Commission. It is defining that the power quality is a set of parameters defining the properties of power supply as delivered to the user in a normal operating conditions in terms of should be continuity of supply, there should be continuity of supply, and characteristics of voltage magnitudes, voltage that is the magnitude, frequency, and waveform. So these are all the definitions of the particular power quality point of view is concerned. So as we have already mentioned, the long-term voltage sustainment, that is over voltages, the equipment nominal operating voltage, if persists for a time duration more than 1 minute, and under voltage, the equipment less than the equipment nominal operating voltage for a time duration more than 1 minute. These are long-standing voltage impressed on the equipment. So naturally, the over voltage issues, if we take up the abrupt load rejection, series parallel harmonic resonance cases, sudden line to ground faults. So these are all the over voltage issues where we have to concentrate. So improper earthing schemes, poor voltage regulation throughout the system, poor voltage regulation. So voltage regulation for any given system, it should be as low as possible. The voltage regulation, if we take up, it is nothing but the voltage drop. It gives the change in the voltage from no load to full load, expressed as the percentage of no load voltage. If the voltage regulation is less, it is a good regulated system. The system is good regulated. So it should have, due to poor voltage regulation throughout the system, this is one of the issue of the over voltage and over compensation of the reactive power, reactive power compensation. To maintain the voltage profile is a separate subject where this becomes an issue of the over voltage and the power, reactive power, overcompensation of the reactive power support provided by the capacitor banks. So these are all the issues where we have to focus, where we have to concentrate the over voltage issues. Coming to the under voltage issues, an increase in the system losses and results in voltage stability problems, motor starting problems, and protection relay tripping. So these are all come under voltage issues. These are all come under voltage issues. Next, voltage unbalance. So the voltage unbalance problem, it is an important power quality issue that can be defined as a condition in a three-phase system in which the RMS magnitudes or phase angles of the fundamental components of the phase voltages are not all equal. That's as I mentioned earlier. The voltage unbalance do occur because of the difference in the magnitudes or phase angles of these corresponding voltages in a particular system. So the principal reason of voltage unbalance in a system is unbalanced loads. So in a particular phase, you will be having Z1 at an angle phi1. In the second, you will be having Z2 at an angle phi2. In the third one, you will be having Z3 at an angle phi3, etc. So on this, you will be having the case of voltage unbalance, a peculiar problem of the power quality. And voltage sag, so it is a reduction in the RMS voltage from 0.1 to 0.9 per unit for a period of 0.5 cycles to 1 minute. It is categorized into three types according to its time duration. What are they? The instantaneous one, the momentary one, the temporary sag. So instantaneous sag, momentary sag, and the temporary sag based upon the time duration. Based upon the time duration, they can be categorized as instantaneous sag, momentary sag, and temporary sag. So this is the taken from the reference IEEE 1159. So this voltage sag results from sudden system faults and switching events of large loads having excessive starting current, such as large motors. So these are all the reasons why do these things to occur. The voltage sags, why do these occur? So swell, a rise in the root mean square voltage for a period range from 0.5 cycles to 1 minute in the course of 0.5 cycle to 1 minute. So these are produced by electric faults, single line to ground, so upstream supply failures, heavy load rejection events, and switching off shunt capacitor banks. So these are categorized according to the time of duration into instantaneous, momentary, and temporary swells. Instantaneous, momentary, and temporary swells, how these can be classified. These can be classified like that. So the interruption, it's a random event. It's a random event with a zero magnitude voltage or current at a particular time period where the magnitude of voltage or current is less than 1.1 per unit, 0.1 per unit. So these are how, depending upon the durations, if it is instantaneous, the type of interruption, if it is instantaneous, it will be taking place, the duration will start at 0.5 cycles and it ends after 30 cycles. 30 cycles means if it is a 50 Hz system, one cycle is 20 milliseconds. So if 0.5 cycles is, it is a 10 milliseconds it occurs. If it is a momentary, it will be, the duration starts at 30 cycles and it ends at 2 seconds. 2 seconds. If it is temporary, it will be starting at 2 seconds and it will be ending at 2 minutes. 2 minutes. So sustained interruption lasts for longer than 2 minutes. It lasts for longer than 2 minutes. So this is how these are categorized. And next, this one is the harmonics. Harmonics. So if we take up any periodically distorted waveform, it can be represented as a sum of pure sine waves. Even using your Fourier transform, it is possible to represent as a sum of pure sine waves in which the frequency of each sinusoid is an integral multiple of the fundamental frequency of the distorted wave. Is an integral multiple of the fundamental frequency of the distorted wave. So what are the sources of harmonics? Where do the harmonics generate? These are basically magnetic core based equipment. So magnetic core based equipment in electrical machines. Wherever you have electrical machines, they will be constructed by taking the magnetic core as the principal material. So by considering this magnetic core based equipment like motors, transformers, and generators, they will have the dynamic excitation system. In the case of alternator, if you have the DC current, the DC field is provided to the field for its excitation, for the strengthening of the magnetic field. The excitation is provided by means of DC field current. So this will give more flux. Due to this excitation, the flux will be generated. So this becomes nonlinear at a point of time, which leads to the generation of harmonics. So that's we can see with the help of static magnetization current curve. And next you will be having arc and induction and arc welders. Arc and induction and arc welders cases also we will be having the sources of harmonics. And we have the power electronic based equipment like inverters, rectifiers, SMPS, etc., where do the generation of harmonics will be taking place. And we have shunt elements like the loads and the FACS devices, the varieties of FACS controllers we are having. We are supposed to have from where the generation of harmonics is possibility is there. So what are the effects of these harmonics? These harmonics, there is basically excessive energy losses. So these are associated with the integral multiples of fundamental frequencies. So double the frequency if it is a second order harmonic, triple the frequency, it is a third order harmonic, 4 times the frequency, the fundamental frequency, if it is a fourth order harmonic, etc. As the frequency goes on increasing, you know the core losses of a particular machine, but a particular magnetic core, they depend upon the frequency. The core losses are hysteresis and eddy current losses. They depend upon the frequency content. So as the frequency of these harmonics going on increasing, the corresponding energy losses, as they depend upon the iron losses or core losses, they depend upon the frequency, the corresponding energy losses goes on increasing. They will go increase. So current in the neutral wire with additional losses, which leads to overheating. Overheating in the 3-phase 4-wire system, the current in the neutral wire increases, which leads to the additional losses. So overheating may take place. So there is a possibility for equipment failure and standstill of motors. Motors come to the standstill condition, the overloading of the conductors. The conductors get overloaded, results in the blowing of fuses and blackout of lamps. So these are all the consequences which occur due to these harmonics. And of course, the fourth one is errors in metering of energy consumption. So there may be errors in the meters while we measuring the particular quantities. and the interference, they interfere with the telecommunication systems and the networks. So there is interference problem with the telecommunication systems and the other communication networks also. So there is a problem of harmonic resonance. So you have the series and parallel harmonic resonance will occur in the case of these harmonic effects. So you have harmonic instability, which leads to damage of generator shaft. So if the stability point of view is concerned, this harmonics, due to these harmonics, they lead to instability, and which leads to damage of the generator shaft, alternator shaft. So there is a scope for noise in the transformer due to these harmonics. The noise that coming out from the transformer can be expected due to these harmonics only, and also in the rotating machines and motor vibrations. So taking all these facts into account, so there is a large scope. There is a large scope to develop a particular model using our interested software like MATLAB or any other software. There is a scope to develop a model, a system, and the system should impose of varieties of components like machines or power electronic components, and we can impose any power quality issue like harmonics generation, and these harmonics can be mitigated by using harmonics nullifying techniques, by using certain filters. Then it become a good project. Then they become a good project. We can focus on these things. We can focus on these things. Any new model, what is supposed to take place, taking the help of the machines, power systems, power electronics, anything, you can build up a model, and we can generate the harmonics, and we should be in a position to reduce the harmonics by using these solutions. The solutions are harmonic filters, active, passive, and hybrid filters. So by putting inline reactors, chokes, zigzag reactors, and harmonic mitigating and K-factor transformer, and neutral blocking filters, and negative sequence reduction by doing negative sequence reduction, and multi-level converters. So we know we are in a position to find the source of the harmonics, where do they generate, and we know the effects of harmonics, and by this time we know the different solution methodologies that are adopted for the mitigation of these harmonics, and of course selective harmonic elimination techniques are also available. Whatever the harmonic we want to reduce, those particular harmonics can be selectively, we can reduce them. So by taking all these things into account, if you are in a position to build up a good model, a good system where the harmonic generation is possible by the introduction of our magnetic cores or power electronic converters or anything else, and these generation of harmonics, once if these are mitigated, if these are reduced by means of using these solution techniques, then there is a good scope for the a good paper or good project. There is a good scope. Next one, if you go for a phase sequence regarding these harmonics, so if you take up a balanced three-phase power system, so the currents in ABC, phases ABC are shifted in time by plus or minus 120 degrees of the fundamental. So this is theta. So this is minus 2 pi by 3. This is plus 2 pi by 3. So this is theta. This is minus 2 pi by 3. This is plus 2 pi by 3. Now, by using the Fourier expansion, if you expand the first three terms of all the three phases, this becomes I1 sine omega 1 t theta 1. This I2 times sine 2 times omega 1 t plus theta 2, I3 sin 3 omega 1 theta t plus theta 3, and similarly IB like this, and similarly IC like this, So if you see these three terms, this term, and this term, there is a phase displacement of 120 degrees, and they are in a particular sequence known as a positive sequence harmonics. These are mentioned as positive sequence harmonics. And if we take up the second one, this one, and this one, there is opposite phase rotation when compared with the first one. The second one, there is opposite phase rotation, which is called negative sequence harmonics. And of course, in the third one, there is no phase rotation, there is 0 degrees, there is no phase rotation. These are called zero sequence harmonics, what we call. So based upon this, we said that the first harmonic is a positive sequence. The first harmonic is the fundamental is a positive sequence because phase B lags phase A by 120 degrees and phase C leads phase A by 120 degrees. Next, as I have shown you, the second harmonic is the negative sequence ACB because phase B leads phase A by 120 degrees and phase C lags phase A by 120 degrees. And the final one, the third harmonic, is zero sequence because all three phases have the same phase angle. All the three phases are having. So if you take up the rotation sequences according to this harmonic number, these particular sequences, these particular harmonics, the fundamental 7th, 13th, and 19th, they rotate with the fundamental one. Next, the third one, the zero sequence, 3rd, 9th, 15th, and 21st, they do not rotate. Next, the 5th, 11th, 17th, and 23rd, these rotate against the fundamental. So due to which we call them as the negative sequence harmonics. And if we take up in the game of a table, the corresponding phase sequence of the harmonics, in the case of a balanced three-phase system, if we take up the fundamental harmonic with the positive sequence, the second one is negative 0, positive, negative 0. So this is how the harmonics and the corresponding phase sequence can be shown. If a particular system is not balanced, then each harmonic can have positive, negative, and 0 components. If it's not balanced one, then we shall have a positive, negative, and 0 components what we are having. So next one, I am going to have so total. I would like to take up an aircraft model, where we have a generator. And this generator is connected to an AC bus and to a DC bus through the loads. These are all the loads: AC1, AC2, AC3, and this through DC1, DC2, DC3, and battery. So these are all these loads are operated in this sequential load factor, in this sequential cycle, what we call. So they will be on some period, they will be off some period, they will be on, they will be off certain periods, like that. Due to which the line-to-line voltage of the generator obtained will be somewhat distorted. Means it is supposed to having the harmonic content. It is having. So here I would like to evaluate. The power quality within this network under various conditions. So for this, I make use of the sim power systems and MATLAB to automatic calculation of the total harmonic distortion. What is the total harmonic distortion? So this is the distorted wave supposed to have, and by using the FFT analysis, I can able to .73%. Then interactively, I may use the particular command power FFT scope here. So here, I would like to take up the model. So this is the aircraft power network model, where I suppose it to have this generator, and this is connected to this bus to AC power distribution network. So from here, this is taken the corresponding DC loads and the AC loads. These are all the AC loads and these are the DC loads, where we have inside are supposed to have a transformer and a rectifier unit. The transformer AC will be taken, and this AC output will be given to the rectifier to convert to DC, where DC lamps and heater etc. can be put on. There they can be switched on and off as shown in the load cycle. So this is the system. This is the system what I supposed to have. So from this system, what I have is, so this is the distorted waveform I obtained when the line to line generated voltage is taken into account. So this is the distorted waveform supposed to have. So this is taken under examination for the FFT analysis. And once the FFT analysis has been taken over, there is supposed to have the total harmonic distortion of 2.73%. So by means of reducing the THD, the total harmonic distortion, we are in a position to improve the quality of the power and to reduce the harmonic content. So by means of employing good harmonic mitigating techniques, so whatever I have suggested in the presentation, by taking the help of them, we are supposed to reduce the harmonics to a possible extent, so that the corresponding output waveform should be as more sinusoidal as possible to the application point of view is concerned. So these are all the things where actually the time duration that is given is 1 hour. So I focused basically the power quality issues. What are the issues under this power quality? And later I have taken the corresponding harmonics, the sources of harmonics, and of course the mitigation techniques, and later on the simple model which I have taken and how to analyze that particular model I have done. So this is all the presentation. So if you have any query,